You sit down with a pencil and paper. You write some symbols,
Numbers, letters.
Greek characters. You follow rules you invented, rules that exist only in your mind. You push the symbols around according to these rules. And somehow at the end of this process, you get an answer about the physical world, about atoms, about planets, about light. The symbols told you something true about reality. How is that possible? Mathematics is a game we play with marks on paper. It has no physical existence. You cannot touch an equation. You cannot weigh a theorem. Numbers do not live anywhere. They are abstractions, concepts, ideas. And yet when physicists write down mathematical equations, those equations describe reality with extraordinary precision. Not approximately,
Not kind of.
precisely, to 10 decimal places, to 12 decimal places. The mathematics predicts exactly what will happen in an experiment before anyone does the experiment. This is strange, very strange. Eugene Wigner, one of the great physicists and mathematicians of the 20th century, wrote a famous paper about this in 1960. He called it the unreasonable effectiveness of mathematics in the natural sciences. Unreasonable. That is the key word. There is no reason this should work. Mathematics is invented by humans. Physics is discovered by humans. Mathematics is in our heads. Physics is out there in the world. These are different categories, different types of things, and yet they match
Perfectly.
Here is an example. Isaac Newton sat in his study in the 1600s thinking about how objects move. He invented calculus, a set of rules for handling continuously changing quantities, purely mathematical rules, abstract manipulations. Then he applied these rules to the motion of planets, and the rules worked. They predicted where Mars would be 6 months from now, where Jupiter would be a year from now. The mathematics that Newton invented in his head to solve a problem matched the behavior of massive rocks flying through space millions of miles away. Why? Another example. Paul Dirac in 1928 wrote down an equation. He was trying to make quantum mechanics consistent with special relativity. He combined two theories using pure mathematical reasoning.
Out of his equation fell a prediction.
There must exist a particle identical to the electron but with opposite charge. Antimatter. Dirac did not look for antimatter. He did not do an experiment. He just followed the mathematics. And 4 years later, experimenters found the positron, the anti-electron, exactly as the equation predicted. The math knew something about the universe that no human knew. This happens over and over. Maxwell's equations predicted electromagnetic waves before anyone detected radio waves. Einstein's equations predicted black holes decades before anyone found one. Quantum field theory predicted the Higgs boson 50 years before the Large Hadron Collider confirmed it. The pattern is always the same. A physicist writes down some mathematics. The mathematics says something must exist or something must happen, and reality obeys every single time. Why does reality obey mathematics? Mathematics is not magic. It is not handed down from the gods. It is a tool humans invented. We made it up. We could have invented different mathematics, different rules, different symbols. And yet the mathematics we happen to invent describes the universe.
Not just describes, predicts.
It tells us things we did not know, things no one could have guessed. As if the universe is reading our equations and deciding to follow them. Wigner said this is a miracle, not a religious miracle, a logical miracle, something that should not be possible but is. He wrote that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and there is no rational explanation for it. No rational explanation.
Coming from a physicist.
Coming from someone who used mathematics every day of his professional life. He could not explain why it worked. He just knew that it did. Some people are not bothered by this. They say mathematics works because we designed it to work. We looked at the world and we invented mathematics that fits the world, like making a key for a lock. You shape the key to match the lock. Of course it works. But this explanation fails immediately. Because mathematics does not just fit the world we can see, it predicts the world we have not seen yet. It predicts things that seem impossible. It predicts particles that should not exist, forces that should not be there, behaviors that violate common sense. And then when we find those things. The key does not just open the lock. The key tells you there is a second lock in the basement you did not know existed. And when you go to the basement, there it is. And the key opens that lock too. This is not how tools usually work. A hammer does not tell you about nails you have not encountered. A map does not show you roads that have not been built yet. But mathematics does. Mathematics reaches ahead of experience. It goes beyond what we put into it. And that is the mystery. That is what Wigner could not explain. That is what no one has explained. We invent the mathematics, but somehow the mathematics knows more than we do. It knows things about the universe that we have not taught it. As if we built a calculator and the calculator started telling us truths about reality that we never programmed in. Let's look at specific cases where mathematics predicted things that seemed absurd, things no one expected, things that defied intuition, and then reality confirmed the mathematics was right. Start with negative numbers. For most of human history, negative numbers did not exist. You cannot have -3 apples. You cannot hold -5 rocks. Negative quantities made no physical sense. But mathematicians invented them anyway, for convenience, for bookkeeping, to make equations balance. Negative numbers were a trick, a mathematical fiction. Then physicists discovered they needed negative numbers to describe electric charge, positive charge, negative charge, opposite but real. The mathematical fiction turned out to describe something physical, something measurable, something that actually exists. Imaginary numbers are worse, much worse. The square root of -1. This number does not exist. It cannot exist. You cannot multiply any real number by itself and get a negative result. Impossible. So mathematicians invented a new type of number. They called it imaginary because it was not real. They gave it a symbol.
The letter I, and they worked out rules for manipulating I just like regular numbers.
Pure abstraction, pure game playing. Then physicists tried to describe quantum mechanics. And imaginary numbers showed up everywhere.
The wave function.
The thing that describes a quantum particle. It requires imaginary numbers. You cannot write the Schrödinger equation without I. Quantum mechanics, the most successful theory in physics, uses numbers that do not exist to predict things that do exist. How does that make sense? Complex numbers take this further. A complex number has a real part and an imaginary part. 3 plus 4i, completely abstract, invented for mathematical elegance, for solving polynomial equations, nothing to do with the physical world, until physicists realized that every quantum state is a complex number. Every particle, every photon, every electron, described by complex numbers. You cannot do quantum mechanics with real numbers alone. You need the imaginary part. The universe somehow requires mathematics that describes things that are not real in order to predict things that are real. Here is another example. Group theory. Pure mathematics. Developed in the 1800s to study symmetries. Abstract symmetries. Symmetries of equations and geometric objects. Nothing physical, just mathematical structure. Mathematicians explored group theory for its own sake. For beauty, for elegance. Then in the 20th century, physicists discovered that all fundamental forces are described by symmetry groups. The strong force, the weak force, electromagnetism. Each one corresponds to a specific mathematical group. SU3, SU2, 2-1. These groups were sitting there in mathematics textbooks decades before anyone knew they described physical reality. The mathematicians had already worked out all the properties, all the predictions. Physicists just had to match the groups to the forces. The Higgs boson is a perfect example. In the 1960s, physicists were trying to understand how particles get mass. They used group theory. They looked at the symmetries. The mathematics said if you break the symmetry in a specific way, you need an extra field, an extra particle.
The Higgs field, the Higgs boson.
No one had seen this particle. There was no experimental hint it existed, but the mathematics demanded it, so physicists believed it had to be there. They spent 50 years looking for it. They built the most expensive scientific instrument in human history, the Large Hadron Collider. And in 2012, they found it. Exactly where the mathematics said it would be, with exactly the properties the mathematics predicted. The math was right for 50 years before we could check if it was right. Number theory provides even stranger examples. Number theory is the study of integers, whole numbers, 1, 2, 3, 4, prime numbers, divisibility, patterns in arithmetic. This is the purest mathematics, the most abstract, the most removed from physical reality. Mathematicians study number theory because it is beautiful, because the patterns are elegant, not because it describes anything real. And yet number theory shows up in quantum mechanics.
In string theory.
In the distribution of energy levels in atoms, prime numbers appear in the spacing of atomic resonances. Why would prime numbers have anything to do with atoms? Prime numbers are a human concept, a way we organize our counting. Atoms do not count. Atoms do not care about our mathematical games. But somehow, the patterns in prime numbers match patterns in atomic physics. This should not happen. Even more bizarre, there is a connection between the Riemann zeta function and the energy levels of quantum systems. The Riemann zeta function is one of the most important objects in pure mathematics. It involves summing infinite series, taking limits, complex analysis. Nothing to do with physics, just pure mathematical structure. And yet the zeros of the zeta function, the places where it equals 0, match the energy eigenvalues of certain quantum systems. Physicists can use theorems about the zeta function to make predictions about atoms. Mathematicians can use experiments with atoms to test conjectures about the zeta function. Two completely different domains. You can take one abstract, one physical, connect it by mathematics that predates both. Pi shows up everywhere. The ratio of a circle's circumference to its diameter, 3.14159, a number defined by geometry. By circles, you would expect to find pi in problems involving circles.
Wheels, orbits.
Waves, fine. But pi appears in places that have nothing to do with circles. Probability theory, statistics, quantum mechanics. The Heisenberg uncertainty principle contains pi. Why? There are no circles in the uncertainty principle. No rotation, no geometry. Just the fundamental limit on what you can know about a particle. And yet, P is there, not approximately.
Exactly.
This number that comes from circles describes something that has nothing to do with circles. The mathematical constant E is similar. 2.718. It comes from compound interest, from exponential growth,
From calculus.
abstract mathematical operations. And yet E appears throughout physics. Radioactive decay,
Quantum tunneling.
thermal distributions, the Gaussian curve. Anywhere something natural happens, E shows up. Not because physicists put it there, because the universe put it there. The universe uses the same mathematical constants that mathematicians stumbled upon centuries ago while playing with abstract concepts. This is the pattern. Mathematicians invent something for purely mathematical reasons. Beauty, elegance. Solving a puzzle. Decades or centuries later, physicists discover that this mathematical invention describes physical reality perfectly. Not sort of, not approximately, perfectly, over and over again. This pattern has held for 400 years. Every time mathematics predicts something strange, we eventually find it in nature. Every time. And no one knows why. So why does mathematics work? There have been many attempts to explain this. None of them are fully satisfying. Let's go through the main proposals and see why they fail. First explanation. Mathematics works because we invented it to work. We designed mathematics by looking at nature. We abstracted patterns from the physical world. So of course mathematics describes the physical world. It came from there in the first place. This is the empiricist view. Mathematics is just organized experience. But this cannot be right, because as we just saw, mathematics predicts things we have never experienced. Antimatter, black holes, the Higgs boson. Imaginary numbers. These were not abstracted from nature. They were invented in pure thought, with no reference to physical reality, often invented centuries before the physics. And yet they turned out to describe nature perfectly. You cannot abstract something from experience that you have not experienced yet. The explanation fails. Second explanation, we only notice when mathematics works. There is lots of mathematics that does not describe reality. We just ignore that mathematics. This is selection bias. We remember the hits and forget the misses. Like survivorship bias, we only see the successful predictions. This also fails, because almost all mathematics eventually finds a use in physics. Not just some, almost all. Negative numbers, imaginary numbers, complex analysis, group theory, topology, differential geometry, category theory. Every branch of pure mathematics that mathematicians have developed eventually shows up in physics. Sometimes it takes decades, sometimes centuries, but it shows up. There are very few branches of mathematics that remain purely abstract, and even those might find applications we have not discovered yet. The hit rate is too high. This is not selection bias. This is a real pattern. Third explanation. There are many possible universes. We happen to live in one where mathematics works. In other universes, mathematics does not work. But we could not exist in those universes. So we necessarily find ourselves in a universe where mathematics works. This is the anthropic principle. This explains nothing. It just pushes the question back. Why does any universe have laws that can be described mathematically? Why not chaos? Why not randomness? Why not laws that change? Why not laws that cannot be expressed in any formal system? The anthropic principle says we observe what we observe because we are here to observe it. But it does not explain why the universe has the structure it has. It is not an explanation. It is giving up on explanation. Fourth explanation. Mathematics works because the universe is mathematical. Reality is made of mathematics, not described by mathematics. Made of it. Numbers and equations are not tools we use to understand the world. They are what the world is. This is the Platonic view, or the mathematical universe hypothesis. Max Tegmark is a modern physicist who argues for this. But this just trades one mystery for another. If the universe is mathematics, what does that mean? Where do these mathematical structures exist? In what sense do they exist?
And why this particular mathematics? Why the mathematics we have discovered?
Why not some other mathematics?
And what about consciousness?
Are we mathematics? Is my experience of seeing red a mathematical structure? This raises more questions than it answers. Fifth explanation. Our brains evolved to understand the world. Mathematics is a tool our brains invented. The reason mathematics works is natural selection. Brains that could use mathematics survived. Brains that could not did not. So of course, we find that mathematics works. It is built into our cognitive architecture. This is closer, but it still does not work, because evolution optimized us for survival on the African savanna, throwing spears, finding food, recognizing faces, did not optimize us for understanding quantum mechanics, or black holes, or the structure of space-time at the Planck scale. These things have no relevance to survival, and yet we can understand them. Using mathematics, the mathematics goes far beyond what evolution could have prepared us for, far beyond what we need for survival. Evolution cannot explain why mathematics works at cosmic scales and subatomic scales, scales we never encountered until recently. Sixth explanation. Mathematics works because we keep adjusting it until it works. When an equation does not match experiment, we modify the equation. We add terms. We change parameters. We fit the mathematics to the data. So of course it works. We made it work. This is the instrumentalist view. Mathematics is just a tool we shape to fit the job. This misunderstands how physics works. Physicists do not fit equations to data the way you fit a curve to points. They derive equations from principles, from symmetries, from consistency requirements. The equations are constrained, highly constrained. You cannot just add terms. Every term has to be justified, has to follow from the theory. And when you do this, when you derive an equation from first principles, that equation makes predictions, specific predictions. And those predictions turn out to be right. Before you check them, you are not fitting. You are predicting. Big difference. Seventh explanation. Maybe there is no explanation. Maybe it is just a brute fact. Mathematics works. We do not know why. We may never know why. Accept it and move on. This is the position Wigner ended up in. The position many physicists hold today. But this is deeply unsatisfying. It means giving up. It means admitting there is a fundamental feature of reality that we cannot understand, that we have no framework for understanding. Mathematics is the language of physics. It is the tool we use to describe everything, and we do not know why the tool works. We do not know why the language matches the world. This is not a small gap in our knowledge. This is a crack at the foundation. Some physicists are fine with this. They say physics is about how things work, not why. Describing nature, not explaining it. If mathematics works, use it. Do not worry about why. This is pragmatism. It lets you get on with the job. Calculate, predict,
Build technology.
make progress. But others find this unacceptable. They want to understand. They want to know why reality has this structure, why mathematics and physics connect, what this connection means. Is there a deeper level, a deeper theory, something that would make the connection obvious, something that would make it inevitable? Or is the connection contingent?
Accidental. A feature of our universe that could have been otherwise.
No one knows. Wigner wrote his paper in 1960, more than 60 years ago, and we are no closer to answering his question now than we were then. We have more examples, more successes of mathematics in physics, but no explanation. The mystery remains. The unreasonable effectiveness persists. So here we are. Mathematics works. Your why unreasonably well. And we do not know why. What does this tell us? Maybe it tells us something about the nature of reality. Maybe reality is fundamentally mathematical, not made of stuff. Made of structure, made of relationships, made of patterns. And mathematics is the language of pattern, the study of structure in its purest form. So when we do mathematics, we are exploring the deep structure of reality, not discovering it, not inventing it, exploring it. Or maybe it tells us something about mind.
About consciousness, about how understanding works.
Maybe our minds are tuned to the universe in a way we do not fully grasp. Maybe the ability to understand mathematics is not just a useful trick, not just a survival tool, but something deeper, a resonance, a connection between the structure of thought and the structure of the world. Mind and reality reflecting each other. Or maybe it tells us we are asking the wrong question. Maybe mathematics does not describe the world. Maybe the world does not exist independently of description. Maybe reality and our representation of reality are not two separate things. Maybe they are aspects of the same thing. And mathematics is the place where they meet.
The interface, the border.
The language that lets us navigate between mind and world. These are not answers. These are gestures toward possible answers. Directions to look. But no one has followed these directions far enough to see where they lead. No one has a complete account. No one can explain why mathematics works in a way that is both rigorous and satisfying. What would an explanation look like? What would it need to do? It would need to show why mathematics is necessary, why a universe without mathematics is impossible or incoherent. It would need to explain why this mathematics, why the mathematics we have discovered rather than some other system. It would need to account for the predictive power, why mathematics tells us about things we have not seen, why it reaches beyond experience. and it would need to be testable, or at least constraining. It would need to make predictions itself, to rule out possibilities, to give us something to check. No proposed explanation does all of this, or even most of this. We have hints, intuitions, philosophical arguments, but nothing rigorous, nothing that closes the loop. And maybe that is okay. Maybe some questions do not have answers. Not yet. Maybe we need new concepts, new ways of thinking.
New mathematics.
To understand why mathematics works, we might need mathematics we have not invented yet. That would be ironic. Using mathematics to explain mathematics. But it might be necessary. Or maybe the answer is not mathematical. Maybe it is philosophical, conceptual, about what we mean by explanation, about what we mean by understanding, about the relationship between mind and world. These are questions science alone cannot answer. They require philosophy, careful thought about concepts and categories and what it means to know something. What we do know is this: mathematics works. It has worked for 400 years. Every time we apply mathematics to nature, we get correct answers. Useful answers, predictive answers. This is not a coincidence. This is not luck. This is a deep fact about the universe, maybe the deepest fact. The fact that we can write down equations and those equations tell us true things about reality is remarkable. It should not be taken for granted. It should not be assumed. It is strange, mysterious, wonderful, and we do not understand it. Feynman knew this. He said, if you think you understand quantum mechanics, you do not understand quantum mechanics. The same applies here. If you think you understand why mathematics works, you probably have not thought about it hard enough. The more you think about it, the stranger it becomes. The more miraculous, the more inexplicable. We live in a universe where abstract thought can reveal concrete truth, where symbols on paper can predict the behavior of particles light years away, where equations invented for beauty turn out to describe reality. This is the world we live in, and it is not a world we understand. Not yet. Maybe someday someone will figure it out. Maybe there is an explanation waiting to be found. Or maybe this is one of those things that simply is a brute fact, a feature of existence that admits no further explanation, the place where questions end, where the why stops. Either way, the mystery remains. Mathematics works, and nobody knows why.